Cheyenne, and I was the project lead.
My name is Daniel. I was the hardware coordinator.
Zach Spofford, software architect.
Monte Johnson, I was the single point of contact.
Daewoo Namkong, I am the note taker. And the objective of our project was to create a control system for the robotic arms that the HPS labs at UTD was making. They have two different types of arms, one that's actuated by servos and one that's actuated by muscles. And they have two types of muscles that they work with, SMA, shape memory alloy, and TCP, twisted coil polymer. And our objective was to use the NVIDIA Jetson TX2 to be able to control both of these hands. And so what they wanted from us was to have a couple of different design solutions. For the servos, we needed to have a servo controller, so we used the Pololu Maestro for that. And for the muscles, they wanted us to use two different ways. They wanted us to be able to actuate them with a PWM signal as well as using a DAC. And so what we had was we had our NVIDIA Jetson, and we had to use our communication channels such as SPI, I2C, and UART to be able to communicate to our hardware. So our software design, one of the requirements was to use ROS, which is a robotic operating system. It kind of functions by using multiple nodes that communicate to each other and as services. And so we had to create a lot of those and a file system so that a user could input a force that they wanted the hand to be able to feel at the end. So one thing about these hands is that each of them have a force-sensitive resistor at the tips. So then instead of having a position-based system, we have a force-based system where it'll continue to actuate until it hits a force, and then it'll actuate until it reaches that force. So say you want 300 grams, we have a system that'll shape that until you reach 300 grams. So as you can see on our hardware diagram, we had to create a couple of different PCBs so that we could use PWM and DAC. And for ADC, we wanted to use SPI initially, but we ended up using both I2C and UART using an STM32 as well as an Adafruit. And if you look at the graph towards the end, we can show the results of that. So what you're seeing there is that a user would input about 375 grams of force, and the program would shape it. So you can't really go from 0 to 300 immediately. So it kind of shape it so you slowly get to that point. And then the force-sensitive resistors, you can see on there that there's two lines that as the force increased, the voltage on them decreased, and the Jetson would read that voltage and signal that you're reading a force, kind of slow down, stop actuating as fast as you're actuating. So we had a feedback loop, and then that was enforcing PID gains. And anybody can go into the configuration file and adjust those numbers to be able to have a different configuration. Are there any questions?
Why the Jetson?
That was one of the project requirements. It was to use the Jetson because that's what they were using with their robot in the lab. So that was the use of the Jetson.
Did you do any formal testing, and what were your measurements?
So a lot of the things that happened was that when we were picking our parts, we needed to make sure that the bit resolution was high enough. So in the performance metrics, you can see that for the PWM and the ADC, they wanted us to have at least 100 hertz on all of those.
So I see the metrics. Were those what you achieved, or were those the goals, and did you meet those?
Yeah, those were the ones that we met. Because of there are a couple of ROS limitations that kind of slowed it down, but because we could have done it faster because the Jetson is really powerful, but just because of the ROS limitations, it brought it down to this. But that was an acceptable rate for it to be at. The professor didn't ask for any higher.
All right. Okay, thanks.